It's all you.
Okay. All right, guys, I'm going to go ahead and get started up here. Hopefully everyone can hear me in the room. Apologies for the little technical delays there. Today I learned that you need to power a VGA HDMI adapter, so hopefully you guys can pick that up as well. Thanks for joining me today. We're going to be talking about something I'm very passionate about. Thanks to the ANYCON team for having me here. This is pretty great. Second year, awesome. Real quickly about myself, my name is Jake Valletta. I am a manager. I work in San Francisco, but I'm from the capital region, so it's good to be back. Actually, there's two speakers here from Duanesburg, New York, so that's kind of cool, I think. I've been a Mandiant for 7 years now. I've done a lot of different things at Mandiant, done penetration testing, incident response, teaching external education, vulnerability research, all sorts of fun things. But I really enjoy Android as an operating system, as a learning platform. So today we're going to be talking about that. I included my Twitter handle on here, but I'm not very good at Twitter, so I have a contact me slide at the end that has more information on how you can reach me if you're interested in any things I'm talking about or want to learn more. So just a quick agenda here. We're going to be talking about a security feature on Android called SEAndroid. We're going to be talking about what it is, what it's doing for you in the background, and then we're going to talk about what things looked like before we had SEAndroid. So go back 3 or 4 years and look at the Android ecosystem and how exploitation was then. And then we're going to talk about some new techniques. If, let's say, you're a penetration tester or you're doing any auditing, what does the threat landscape look like now? What are the things you need to keep in mind if you're actually trying to attack a device that is using SEAndroid? And hopefully we have some time for questions and answers. If not, I'll be at the conference all today and tomorrow, so feel free to flag me down and ask me exciting SEAndroid questions. So just some of the goals and hopes and dreams for the people in the audience. First, I want people to just understand what SEAndroid is, and most people probably aren't even aware that it's on your phone. It's kind of just running in the background, doing good things for you. But just understand fundamentally how it works and why it's there, and what it's doing to secure your data. And if this is something you find interesting and want to learn more about, to provide a starting point for you. So if, like I said, if you're a penetration tester, or if you just want to go buy a new phone and start auditing it, what are the tools and techniques you're going to need to use to actually get started? And the last one is kind of tongue-in-cheek here, but is to just really talk about Android security and how it's matured over the years. I've heard a lot of comments, both not just to me, but just in general about Android security, and I think one of them, maybe the most mad, is when someone said the only secure Android phone is when you throw in the trash. And okay, there's some problems with Android, but it's not the worst operating system out there. There's way worse things. Just look at Windows a few years ago. Compare that to the new versions of iOS and Android. I think it's a stark contrast in terms of security. So those are what I'm hoping you guys can get out of this. So let's talk about SEAndroid here. So before we can talk about SEAndroid and how it works, then we need to kind of just do a little bit of formal definitions here in terms of access controls. So everyone is familiar with access controls, whether you know it or not. You use them day in, day out, both in the digital and just in real life. But essentially, it's restricting some sort of subject or person or thing access to an object. The object could be a file, the subject could be a user. That's how computers work. We have two different models here. We have the discretionary access control. A lot of us are familiar with this on Windows and on Linux. By default, those are discretionary access control models, in which the subject can pass control onto other objects. For example, on Linux, if I own a file, I can do as I please with that file, which is good for sharing data, but it can also lead to some security vulnerabilities, which I'll demonstrate here. And it's just a little too permissive on things like Android devices. The other model is called a MAC, or a mandatory access control system, and this is when the policy is governed by a central authority. In most cases, it's going to be the kernel. On iOS and on Android, it's both the kernel who's enforcing this. And owners, even if you own quote-unquote a file, there's really not much you can do to share and change things. I can't just say, hey, I want someone else to have this file. The policy master really is the person who does that dictation there. And just some examples here. Obviously, we're going to be talking about SEAndroid. You can also call it SE4Android or SEAndroid, it doesn't matter. And I also just wanted to conclude on here Trusted BSD, which is the framework that Apple iOS uses. So I want to just kind of point out this isn't just an Android thing. It's also on iOS. It's on many security platforms. So let's take a look at the Linux DAC system, and so just some weaknesses here in terms of how it applies to the mobile ecosystem. So first off, let's say you have a server in your house. You have maybe a couple users for you and your wife, maybe your kids or something, I don't know. You have some processes running on there. Maybe they have users as well. And then you have this sort of like elephant in the room root user, which everyone tells you not to use because it's very powerful, but it's there. And when you are root, you can do whatever you want on the system. And unfortunately, or fortunately, Android is based off of a Linux kernel, which means that this root user is also there on your phone. Even though the Android runtime to play things like Angry Birds don't need root privileges, and they shouldn't, right? It doesn't make any sense. However, a lot of things historically run as root on your phone. Things that you take for granted every day, things like your volume manager, which is mounting and unmounting file systems, or your battery sensor daemon is running probably historically as root. What this leads to is the problem where if a vulnerability is discovered, these are the targets that attackers are looking for, right? They're looking at the volume manager, they're looking at the battery sensor, they're looking at any other sort of privileged process because they're running as root. And once you're root, you can do all sorts of exciting things on the phone. Also, the second point is mostly because I've seen developers do very silly things in the app space. They can do what they want with their files. And maybe that is a good thing, but Google has a whole platform on how to share data securely, but not everyone does that, right? You can do whatever you want with your files because of the way the Linux stack works. Also, things like ioctls, which are calls to the kernel, or Unix sockets, do not have the ability to fit into Linux's DAC model. Right? We can't actually enforce controls on ioctls unless we actually restrict file access to which we're sending the ioctls, which we'll talk about in a few slides. And really, we can't get as fine-grained as we need to. Right? Think about like the volume manager, right? So the volume manager has one purpose. It mounts drives, I guess two purposes. Mounts drives and unmounts drives. Mounts drives and unmounts drives. It does need privileges to do that because it's a very sensitive call, but what else does it need access to? Well, probably nothing. Maybe a configuration file, maybe a couple other files it needs access to, but it doesn't need the entire capabilities of the root process. And it gets very messy in trying to implement that with the traditional Linux stack to actually say, here's what this process can and cannot do. So a lot of us in the room are probably familiar with this. This just illustrates the 9 standard bits for file manipulation and access rights on Linux. You can ignore the D at the beginning, that's just a directory in this case. But we have read, write, and execute. Right? These are our actions here. And we have 3 different subjects. We have the owner of the file, we have the group associated with the file, and then we have this guy over here, other, right? We have the everyone else. This is just the negation of the user and the group. So this is any other user on the system can do things to this file, and I can set these bits freely if I am the owner of the file. So let's walk through an example here. So let's say we have Alice, and Alice wants to store information in a file. And she creates the file, she puts the data in the file that she wants to, and because it's her file, she can do freely with this file. She now wants to share the data with Bob. So Bob can access the file, he can see the data as well. So she can just set the permissions. So Alice, maybe she's not a security person, she's just a developer, or she's just someone, a hobbyist or something. And she sets the other permissions so that Bob can access it. Because she doesn't want to create a group, maybe she doesn't have the ability to create a group. And she just says, all right, anyone else, you can read this file. But maybe what Alice didn't realize there is that by setting the other flag, everyone else besides just Bob can access this file. And now people like Eve, or our attacker here, can now access that file, and Alice has lost her data. Now, I know this sounds silly and contrived, and why would anyone do this? But this is real life, right? This is the applications on your phone doing this. Back in 2013, I did some security testing of a bunch of voicemail applications. So there was this new smart voicemail wave that swept a bunch of carriers where they were taking the audio from your voicemails and transcribing them into text messages and storing them on your phone. That's all fun and games, but they were storing all the files world readable. So any app that was on your phone could just, if it knew the path, access your voicemail, both the WAV files and the audio, or the text data that was transcribed from them. So this is a big deal, right? These are production applications running on a lot of phones, and by default, they're installed by your carrier, right? So companies like Verizon, Sprint, AT&T, they're including these apps on your phone, whether you realize them or not, and they're doing stupid things like this. So this is a problem. So let's talk about how SE Linux can make a difference here. So I said SE Linux because that's sort of like the base project that was created back in the late 80s by the NSA. So it was developed under the name Security Enhancements for Linux. And then in about 2012, it was ported to Android. And they changed the name, and now they call it SEAndroid. But if you called it SE Linux, it's essentially the same thing. The port is different in regards to that they added new features that support the Android ecosystem. So traditionally, SE Linux was mostly for files and other Linux-y things. But there are other things on Android that matter, such as the property subsystem and the system services subsystem that are not part of the SE Linux project, and they don't really need to be. They're really more specific towards Android. So they have ported, and they've actually gone in very separate directions. So Google is no longer committing to the upstream project, which I'll talk about in a few more slides. It's kind of a pain. But anyway, it was introduced into the AOSP. I'll be calling it this for the rest of the slides. This is the Android core developed by Google. The Android open source project is freely available. You can download it, you can build it. It was introduced in 2012, right at the end of the year, when 4.2, what's that? Jelly Bean came out. It wasn't doing anything. It was more like experimental commits. They were just testing things, probably using it internally. In end of Q3 of 2013, we saw SEAndroid move into permissive mode, which we'll talk about in just a slide here. But again, it's not really doing too much at this time. And then in Q4 of 2014, so just about 4 years ago, with the introduction of Lollipop, we saw it switch to enforce mode. So what is permissive mode versus enforce mode? Well, permissive mode was designed so that the OEMs and the developers could test their policies before they actually applied them. Because if they just rolled out this new feature, all of a sudden everyone's phones are just not going to work. Because there's a lot of tuning involved here, a lot of manual analysis that you have to do to figure out who needs access to what, and none of this stuff was mapped out yet. So they put it in permissive mode. Basically, it's logging things, but it's not preventing actions from taking place. With enforce mode, we actually block and optionally log all violations that occur. So if the battery daemon tries to access the network driver, that's going to be blocked, and it's going to be logged potentially so that someone testing can figure it out. And the biggest thing here, the most important thing here, is that this is required by Google's compatibility test suite, which means that if you want to make a phone and have the Play services on it, which is the whole Google runtime, you need to support SE Linux in enforce mode. No questions, no changes, or you'll get in trouble by Google, and you can have your headset revoked or whatever the legal terms are for that. But it's required by Google's compatibility suite, so that's important, and we'll talk about that and some shortcomings there. But I think that's great that Google has done that. It's sad that a lot of people turn it off. So, what are some of the goals here? Right. So, I talked about the root user, and that user needs to go away. There really doesn't need to be any single user on Android, especially when nobody has access to that user. You can't just plug your phone into a Linux machine and then type sudo su and run a command as root because no one has access to root. So no processes should be running as the root user. So one of the goals here is to basically neuter that user. Make it not attractive to try to find processes running as root. Instead, make the context for those processes very restrictive and make it much harder for an attacker. Also, we have all these system daemons. Again, things like the volume manager, the Bluetooth daemon, all these things running, the installer daemon. All these things are high-value targets on Android, and we need to make them much more difficult to gain access to. These guys here, so devices, so device drivers, Unix sockets, all kernel-backed file systems. Why does an application need access to that? That doesn't make any sense for Angry Birds to be able to access the sysfs. Right? Those are kernel structures to view information or set information in the kernel that normal applications need no rights to. Or devices, right? There should be no reason an app to be talking to a device driver. And it's not to say we're going to get rid of the traditional Linux stack. We're actually going to keep everything that was there, and we're just going to bolt this on top of it, which just adds another layer of complexity for an attacker. So my goal here isn't to show you how to write rules. We're not writing rules together. We're not applying rules. I'm not demoing rules. I'm just kind of showing you the format of what a rule looks like so we can talk about how they work when we actually start analyzing the policies on our phones. So the first thing here, everything's going to get a label, all objects, whether it's a file, a process, a a socket, everything gets a label. From here, this is the format. We have our action, which is either allow or deny, whatever. The domain, this is basically the subject. So this is who we're talking about. And so you'll say like, hey, this person here, and then this is the object. Type is going to be the label for our object, so this is something you set. For example, you could call it myfile, which is not a good idea, but you could do that. The class is the category, which is to say these are defined categories by Google, things like files, sockets, I put property service. There's plenty more, but you don't need to edit these. You just basically say this is a file, and that's what you set the class to. And then the permission is the actual operation you're performing on the object. Read, write, open, ioctl, whatever you want to do to that particular class is going to be your permission. So we are going to write one really quick rule here. It's just called my rule. And let's say we're a developer on our phone, and we have this new binary we're introducing. And trust me, OEMs introduce lots of new binaries. And we're calling it my tool. It's in system bin directory, whatever. And it basically has a configuration file that it needs to read from. And it's called mytool.config. So we're going to create an arbitrary label here called mytool_file. And we're going to label this right here. And then we're going to label also the mytool_config file as mytool_config. And then we're going to create a rule to add this mapping in these particular actions that we want it to have. It's very straightforward. Allow mytool file, mytool_config file, read. Right? So now any other operation performed on this file, attempting to write from it, or to it, sorry, attempting to execute it, attempting to do anything else other than issue a read call is going to be denied, and it's going to be logged potentially. So you can see how fine-grained you can get here. You can really have a process that has a very singular task, and make sure that it only can do that one task. And we'll see just how big of a deal that is when we start talking about some of the exploits we see in the wild and why it matters. So rules are defined in these TE files. And if you just Google like SE Linux TE Google source, you'll find a bunch of them on Google's GitHub repos. But there are dozens of TE files, and it's all a boilerplate framework for you. If you just downloaded the Android open source project and you wanted to start building your device, you have a really good starting point. You do need to change things, especially if you start introducing new hardware, new software, but you have a good start. There's all these macros that help you here, and you will need to change it. Like, there's no real questions there. You have to change things to work on your device, and that's going to be to the advantage of the attacker, because the people who are making the changes are not Google, and are not people who do this probably day in and day out and breed security. Just to illustrate the process here, we have all of our TE files, which are rules, all of our definitions up here. This is like this black box here that bundles it all up, compiles it, and out pops this little tool here, which is loaded on your phone. It's a binary file called sepolicy, and it's sitting in a directory on your phone with all the rules inside of it. And the kernel is going to load that guy up, and that's what it's going to check every time it wants to do any sort of action on the phone. It's going to come into play when we actually start looking at any particular device. So let's look at what it looked like before. And I have a couple of case studies here that I think illustrate sort of the shortcomings of Android. So it used to be, as I've kind of mentioned a couple times now, a race to root. Right? It was as soon as you got root code execution, the game was over, and you just would root the phone, install a rootkit, do what you wanted to. And in my experience, this is 1 to 2 exploits. Right? We're not looking at anything crazy, especially in the early days. And you could pretty much do what you wanted to on the phone. Like for this, root users can load kernel modules. That's probably not something that any production phone even needs to support at this point. In some phones it's turned off, but the fact that the root user is there and can do that is a problem. And again, as I mentioned numerous times now, a majority of the Android core processes outside of things running Angry Birds are running as root. So there's a huge attack surface here. So we're going to go back to 2011 here and talk about the GingerBreak vulnerability, which affected Gingerbread, which is so long ago, but still worth talking about. This was one exploit that exploited the volume manager daemon, which I've already brought up, which was running as root. That is essentially designed for when you plug in an SD card. Remember when phones had SD cards? Or when you plug in USB and you want to mount a drive, the volume manager takes over and says, yep, I'll apply this for you, I'll format things for you. The problem is there was some issues with it, particularly an exposed netlink socket, which I'm not going to spend too much time talking about the whole exploit chain here. This is already documented. I didn't find this. Other people did. But essentially you have this socket that you can open here of a netlink type, and you just send a message to this socket, which is linked up with the kernel, and then it does something which ultimately leads you to be able to introduce a setuid binary. And for all the security folk in the room, know what happens when we have setuid binaries that we control. The game's over, right? We can execute that and get root. So let's look at this if we compare it with SEAndroid. So a lot of these actions, almost all of them, are completely just neutered, right? We no longer can open netlink sockets. Sorry, that's just not a thing anymore, right? You shouldn't have been able to do that anyway. I don't know why you would have been, but you just can't do that anymore. Even things like catting files in the proc directory. There's no reason why a process should be trying to figure out its command line by accessing the proc file system. There are other APIs that can be used for that, if you needed to do that. Just doing things like walking offset tables. Nope, can't do that anymore. These actions right here, like being able to call remount, just not going to work in this context. You can still do setuid, although this has changed a lot in more recent versions of Android. However, you're still running in the same context after you setuid, so it probably doesn't really matter too much. So completely removed, even if the vulnerability still existed on the phone today. How about weak sauce? This was a few years later, 2014, reported by John Sawyer, or JCase on Twitter. He's a very popular, very loud person on Twitter who talks about vulnerabilities. If you're interested in a lot of his work on early Android exploitation, it was very inspiring for me to learn about these things. But this particular vulnerability affected HTC devices, and it was local privilege escalation to root using a Unix socket. So again, we're noticing a trend here. I've given talks just on Unix sockets and how silly they are, but the truth is everyone uses Unix sockets on Android because they need it for IPC in the Linux space. This one was so ridiculous. It was just a Unix socket that there was actually a driver that was loaded that had a function called like move file, and it would execute it as like the kernel context. So any application with the internet permission, which let's be honest, every application needs the internet nowadays, could literally just move and copy files and do things to escalate privileges. So we're talking one exploit here, one single thing to go from the lowest privilege app with the internet permission to complete control of your phone. Now, of course, this is fixed, but here's the big thing. It was accessing a Unix socket in the dev socket directory. There's no reason any application should be interacting with those. This was for HTC to do some privileged things. I don't really know what they were trying to do here. But there's no reason an app should be interacting at all, even reading from that directory. So this whole vector, this whole suite of vulnerabilities has effectively been mitigated as an unprivileged app just because you can't even ls anything in the dev directory. And that's good. That makes me feel good about things. A few years later, this is one that I actually reported to Qualcomm. This one was a vulnerability in the netd daemon, which was in Qualcomm specific firmware branches, which is still millions of devices. Millions of devices. This was around for a long time. So I found this in 2015, but chances are this guy was hanging around for quite a while. Now this isn't code execution as root, in this case it's radio, but the radio user is a privileged user on Android. Notably, it has access to the baseband, which can lead to all sorts of other issues there. Again, we're talking one exploit as a third-party application to be able to access the baseband. So this particular vulnerability, besides just accessing the baseband, it could also allow you to read and write SMS. Again, why does the netd daemon is responsible for assigning IP addresses, managing your DHCP leases. Why can that read and write your SMS database? Well, they didn't have a way to say that this particular process needs to run privileged, but can't do these actions, so we have this huge attack surface. It can also do file system activities that should, like, it can write to directories on areas that it really had no right being able to do, and it had really good access to the property subsystem, which we'll see comes into play a little later. The property subsystem is essentially like the Windows registry, and also with events that you can trigger on when interactions are made there, so you can set up alerts for when this property changes, do this particular action, which is really fun if we can actually make changes to those properties. So let's look at this with SEAndroid. Well, this one's fixed, right? You just can't do that anymore because the netd daemon is running under a policy that doesn't let it access the context anymore. That's good, right? The baseband, you can still access it. Unfortunately, there's really not much you can do about that because it's designed to interact with the radio. The file system access has been revoked, so you wouldn't be able to do that. Unfortunately, you can still alter and influence the network stack because, again, this is the networking daemon. And the property subsystem has been completely revamped with the introduction of SE Linux or SEAndroid. So that has changed and is much more restrictive now. And then there's one last caveat here I just want to point out. And that is basically that not everything's changed, right? A lot of embedded devices that aren't Google-sponsored phones are running Android. Things that you don't even probably realize, like conference phones are all Android-based now. Even your cars are running Android Auto. Children's toys, I've tested a lot of children's toys. Oh my God. And just insert random IoT device, right? Anything, like even I'm sure refrigerators are running like Linux or Android. And the truth is, like the cold, hard truth is, people are just turning this off. Because if they don't need to use it and they don't want to develop it, they're just shutting it off. And I've seen this numerous times, and I put it as finding blocks in reports, like, hey, you straight up just turn this off, and it's just, no one budges, because it's hard, right? You have to do a lot of tuning, and all these developers, especially ones who are coming out of China, no offense, are just not thinking about security as the forefront. They're trying to push a product, an $80 children's tablet that I don't know what it lets you do, have your kids learn or something, is they don't care about SE Linux, they don't care about SEAndroid. Everything is running on root on those phones. Like, it doesn't matter. We're back in 1998 again here, and it's very easy to compromise anything that's not a Google-sponsored phone. Okay, with that out of the way, let's talk about modern devices and what it looks like. So, when I was doing some work previously, a coworker of mine commented on when I wrote up an exploit chain for a vulnerability. He was like, "Man, this looks a lot like a Rube-Goldberg machine." And I was like, what's that? So I looked it up, and if anyone's played like Mousetrap before, like where like the ball hits the lever, which lights a candle, which like triggers, it's like all these different actions that have to occur. That's kind of what we're dealing with now, right? That's the reality of what it looks like now, where it's not just let's run exploit and we're root over here. We have to do all these silly things, jumping from context to context potentially, just to get the rights we need to do a specific action. So we have to ask ourselves different questions. No longer ls and run, or ps and run grep for root. That's not going to work anymore. What we need to think about is, what's our objective? Are we trying to write to the SMS database? Because then we need to focus on context and have access to that. Are we trying to release an exploit that gives us root privileges so we can actually install malware? Well, you have to focus on context or target a context that has access to that. The user doesn't matter anymore. You could have a really low privilege user that has all sorts of SEAndroid modifiers, which give it more rights than you had before. And then my favorite things to talk about are changes by the OEMs. It changes to the Android open source project, because this is where the bugs are sitting. I've talked about this for years, and I've reported dozens of vulnerabilities in vendors like HTC, Qualcomm, LG. These guys are not as good at security as Google has been in protecting their code. And that's just my opinion, but I mean, that's what I've seen, that's where I'm staying. So I like to focus on the differences. So if I have a Huawei phone, what's different? Let's look at the Android policy, the SE Linux policy, and say, what changes have they made? Because you'll see glaring changes. Even if, so like some of the ones that are forced to turn it on, that doesn't mean they can't tweak it and change the way things work, right? They can't figure something out, they'll just slap on a modifier that gives that process full rights. So, okay. So let's say we're getting into some more technical details here. Let's say we actually we have a phone that our friend has given us, we want to start looking at it. The very first thing you need to do is you need to get access to the policy files and the labeling files. These are all going to be present on the phone. On most phones, they are accessible. The biggest one here is SE policy. SE policy is that binary file that's loaded up by the kernel, which tells you all the rules that are going to be performed. The rest of these are just for labeling, right? So this is the file context, which was in binary format for one version of Android. It's going to have the mappings from a file name to a context. Same thing for services. Service name to a context. Properties to a context. You get the idea. Last one here is an XML file that has our labeling for applications. So this is how applications need to behave, because even applications get labels now. To pull these off, you can use the Android debug bridge, which I'm not going to spend too much time talking about, but you can interact with your phone using this as a shell user. If you have a firmware dump, you can also pull them out of that. I've used that in the past where maybe I can't get to the SEAndroid files because sometimes they're just not accessible, but you get them from a firmware dump. Most of these files are clear text and super easy to understand, with the exception of the file context, which was converted to a binary format in NuGet, and then they immediately switched it back. I couldn't find any parsers that were written not in C hosted on Chinese forums, so I wrote one in Python, and it's on my GitHub. If for some reason you're testing a NuGet phone and it's using the binary policies file, or sorry, the binary context file, it's just a simple script that just parses the structure. It's pretty straightforward. Now, unfortunately, this sepolicy file, which is a binary format through and through, is a completely different story. So we're going to circle back really quickly here. I just want to show you how this works. Let's say you run an ADB shell command. So this is specifically for the Huawei Honor, running, in this case, I believe this is NuGet. I'm running ADB shell, and then I'm running the ID command, and you can see my context is nested right down here at the bottom. After all my traditional Linux DAC things here, all the groups and users I'm in, here's my context. I'm running as a shell context. So that's a good starting point, right? If we're going to start poking around on this phone, we need to assume we're starting as the shell context. Not so much the shell user. Obviously, that's still important as well. But knowing that we're running as the shell context is key, because that's the access we have. Okay, so we have our context. Now we got to parse that sepolicy file. I encourage you, go on Google and type in parsing sepolicy Android. You're going to get this link right here. It's on Stack Overflow. It's like 4 years old. And it's someone saying, hey, I just want to parse this file. Can someone please help me? And this guy says, well, I've been looking into this. You think this would be easy? Blah, blah, blah. He starts talking about it. And really it comes down to because Google has forked the code. They're kind of doing all this stuff behind the scenes. And they're not really publishing the tools that a normal user would use to search sepolicy, because why would they? Because OEMs don't need this. They have their own testing suites. And the only person who needs this is me, who doesn't have access to the source code, who doesn't have access to the TE files. This is stuff for attackers, and they're just not publishing that. So I reached out to the GitHub guy who is maintaining the SE policy, well, mostly just the SE Linux fork of Android, or actually, sorry, the mainstream project, the mainstream SE Linux. And I said, hey, this is a great tool, it's really helpful. Like, what are your plans to support Android? And he very kindly replied the next day and said, hey, I have no plans of doing this, so thanks anyway, and he closed it. So basically, we're not going to get any mainstream support for sepolicy parsing, which sucks. So let's go back to this guy here. This is his start of his question, or his answer. Well, here's his answer. Well, all you have to do is first clone Android, which is about 70 gigs last time I checked, and then set up a build environment, which is probably a day or two of work. Yeah, and then you download this other tool and make these changes to these 4 files, install these dependencies. By the way, if these don't work, there's some alternate instructions here. Then you can finally do these other operations here, which will help you build some other core libraries. Yeah, so you can do all these things, and it actually works. So if you take the time to do, as I say, Google this is the process right now. Right? This is the way things work, unfortunately. Once you have the binaries and the bindings, you can share them with your friends or whatever, but the trick here is you need to get access to do all these steps just to be able to run the SE search command, which in its glory is here. So the SE search command is going to be a way for us to take the policy file, which is binary, and then run searches for the context we care about. Really straightforward, easy example here. I'm going to search the sepolicy file for that Honor, that Huawei phone. Show me all the files that I can write to as the shell context. Here they are. Here are all the labels that I have access to where I have the write privilege. And then do that additional layer here. Look for the things that are different. How about the Huawei sensor label? Right, this is some new sensor, new label that was not part of Android. It's a very easy process to do the diffs here. You can just basically diff this list. And these things will stand out. This one even says Huawei in it, so it's even easier. Well, what is that? I have no idea. Let's find out. Let's find out all the files that are labeled as sysfs Huawei sensor. And look at this. These are all, again, on the kernel backed file system, sysfs, in the sys directory. These are direct interfaces to read and write to potentially the kernel, which in itself is not a vulnerability, right? It's just an avenue for an attacker to now, as an unprivileged user, potentially interface with the kernel, send data to it, receive data from it, what have you. So each one of these will need to be investigated. Well, what can we do with the Huawei ALS info structure? I don't know. But this is the process you take. You find a context, you map it to things like files, but again, properties are going to be important, services are going to be important, and you're going to want to look through what exactly this context can do, and it may not be beneficial to go straight for the gold, right? You might not be able to find a context that has access to something super sensitive, which means you're going to have to go back to that Rube-Goldberg machine-like model where you have to jump around. Maybe you just take baby steps, get yourself into a platform app first, and then focus on something more advanced. Did I skip something? No. The property subsystem is also, like I said, really instrumental and key to the Android model. And there are some properties that you should be aware of that if you're in these if you have access to this context, then you're going to already have code execution or some sort of privilege escalation. That would be the system prop one. If you can get a context that has this, you got a lot of surface that you can now cover because you can now interact with a lot of system properties that normal apps are not expected to be able to access. So you can make all sorts of funky changes to properties that other processes are loading from, and additionally also maybe look for those triggers I was telling you about where you can actually have actions occur when you modify properties. Also, the default CTL prop label is the label required to start and stop init services. Init services mostly run as roots though, and they're not usually labeled with very restrictive labels because they're just not, unfortunately. So getting in one of these two is going to be really big. Again, look for non-AOSP properties. Here's an example right here. This is me running the SE search, and I'm looking for, if I'm the netd daemon, so let's say we exploited my Qualcomm bug here, and we're looking for properties that we can set on the Huawei Honor. We can set all sorts of stuff. In addition to read-only ones, which are kind of fun, right? Why would you be able to write to read-only ones? But that's kind of how things look here. Also, all of these ones down here, these are all non-Android open source. These are all added by Huawei, right? So now, if I exploit this Qualcomm bug, I can now modify the camera tuning dump property, which again, no, I'm not sure what that does, but now you take this as a starting point, start reverse engineering the binaries associated with these, and we're looking at these, and you may have command injection, you may be able to overwrite additional files, all sorts of exciting things. This one, this RO Huawei one just lights me up. The fact that it's read-only and process can write to it. But anyway. Also, there's another avenue you can take. If your goal is to just kind of map out the context, look for ones that have what are called capabilities in SE Linux. So capabilities are these like power features that you can just tack onto a process that let you do all sorts of good things. So how about DAC override? Right, we talked about what DACs are, and I mentioned that we're going to use the old Linux DAC, and then we're just going to bolt this on top. Now, you have a context with DAC override, none of those rules apply in the kernel level. It doesn't matter if the file is readable as anyone, if you have DAC override, you can read that file. DAC override read obviously is just for reading. Sys module, we can now granularly enforce if kernel modules are loadable by having the sys module capability. But as you can see down here, I'm looking for all the contexts that have the sys module, and the netd capability, or netd daemon has the ability to load kernel modules. Or how about this, looks like maybe a Wi-Fi driver or something. So there's still avenues here that can be used. And for those of you not familiar with kernel modules, it just lets you load code into Linux kernel. Once you can do that, it's, again, game over, because we can directly call code from the kernel. Fowner, this one lets you basically do, it just kind of destroys the file permissions, very similar to DAC override. And some of these are just like super privileged, right? I have this, I think this is the Huawei networking daemon here. This thing can do everything, right? So basically what this is saying is, don't worry about this process. Just don't apply the SEAndroid policies to it. It can do pretty much whatever it wants. So these are your high-value targets. These are things you're going to want to look into. Any particular phone is going to have a number of these that you should actually focus on. So I wanted to kind of wrap this up. I know we're a few minutes left here, and just do a little quick case study. So in 2016, early 2016, I found a bunch of bugs in Lenovo phones that they tried to downplay it, but it affected like 60 other different models, mostly international, that gave you root code execution, also a privileged context. So not only could we have root code execution, we also had it in a very privileged context. And it was kind of fun to report this to them. They were like, wow, that's kind of creative. Like, yeah, you guys like wrote this shitty code here. But anyway, we reported it to them, and they were receptive eventually. And we finally got a chance to blog about it. It's on the FireEye blog if you want to learn more. I wrote this article, I'm pretty proud of it. And it talks about, in very technical detail, how we went through in each of these CVEs that were assigned, what they are, how they work, how they play the thing. So I'm going to talk about it very briefly here. But essentially, it's code execution as root through a semi-protected Unix socket. So again, everything kind of comes back to these same core fundamentals. Things like Unix sockets, sysfs's, they're really the targets we want to focus on. What we found is that there's this process. NAC server is running as root. It's running in a fairly privileged SE Linux, SEAndroid context. It listens on a local Unix socket. For those of you not familiar with Unix sockets, it's really just a socket without IP addresses. It's just some sort of way to communicate between processes. And I kid you not, the purpose of this daemon is to receive a command on the Unix socket and execute it. This is the literal definition of a backdoor, and this was on every Lenovo phone worldwide. So, just let's pretend that SE Linux is not around. Let's say we didn't have it. One vulnerability, game over. Right? We're already done. We have a process running as root. It's the same thing as an HTC vulnerability that John Sawyer reported in 2014, but this one was on every Lenovo phone. However, there was SEAndroid on the phone that I had, which means we had to jump around a little bit. We couldn't just interact with the Unix socket because, as you see here, if I try to connect to it using just SOCAT or something, I get permission denied. And then if you cat the kernel buffers, you'll see that yes, there has been a SE Linux or SEAndroid violation. You cannot access this abstract socket. That's wonderful, but who can access that socket? That's our very next question, is if I can't do it, who can? Well, turns out if you're a system app or a platform app, you can do that. And there's about 60 or 70 platform apps on the phone that I was testing. This was the Lenovo 5, by the way. So now our target's shifted. Now we're just going to find any running process that's labeled as platform app. And here's one right here. The Idea Friend application. This was their Lenovo's implementation of the Contacts app, which had a nice little bug in it where they basically loaded jars at runtime that were unsigned and executed code from them, so we could create a backup of the app and then modify the jars, and then it would reload them and run them. So it gave us code execution as a platform app, which is wonderful. So now we can talk to that socket. Here's just a fun little picture of us running the vulnerability, or the exploit here. We basically create a bunch of custom backups here, stage our payload, and then we can trigger the bug by talking to the Unix socket, sending it a command for it to run, and lo and behold, we have a shell that's root here with this context called root channel. So like they even knew what this was. They labeled it as root channel because this was meant to run root commands. Now again, it's not a complete compromise. In my mind, it was job well done. You can do a lot, but there's a few things you couldn't do. For example, you really couldn't mess with the kernel too much. So we can't turn off SEAndroid. That's great. That's actually pretty good. And you couldn't remount file systems. So we couldn't create like a persistent backdoor on the phone. But again, we probably would just need one more bug from here. And with Lenovo, I don't think that would be too much of a problem. We could find some driver that has an issue with it. And with that, I want to kind of close things up here. So just to wrap up, if you have a phone that is sponsored or approved by Google that was released after 2014, there's a very strong chance that your phone is protected by SEAndroid. And that's great. You don't have to do anything. You don't even know that it's there. You don't need to know. It's really changed the way the attack surface looks on phones, and it's changed what attackers are looking for. And I didn't put it on here as another wrap-up item, but messing with this stuff is kind of a pain because you have to go through this lengthy build process to get the binaries that you need to actually run the queries. But from there, it's just using the SE search binary to dig around and look for exciting things on your phone. The exploitation process is really no longer just find root and then exploit it, which for the longest time is what I would do. I would just do PS, rep for root, and then I would look at Unix sockets and find which ones map to each other, and then I would just fuzz that Unix socket until we figured out what it did. We can't really do that anymore, which is good. We don't want that to be the case, unless OEMs are disabling SEAndroid, which I can assure you that they are. With that, here are some additional resources. So if you want to learn more, first, definitely start with this slide. This slide deck here, the case for security enhanced Android. This was written by a guy at the NSA, basically championing SEAndroid, saying, hey, this is why we need this. He goes through, I think, like 4 or 5 case studies about why this is important, why it's beneficial. Very good starting point, really illustrates similar to the case studies I went through, but you'll get a lot of good information there. Last year, I got a chance to see Nick Kay at Google talk about why he's the head of security on Android, and he was talking about why they've decided to use SEAndroid and sort of their motivations and what they see on the Google side, which, again, I don't work at Google, I'm not sponsored by Google, but this is a great idea, and it works very well. I also recommend checking that out. You can find that online. The rest of these are just technical blogs. These guys right here, oh man, if you want to learn all the functions that have been modified in the Linux kernel to support this, those are your slides right there. The Android documentation is also quite good, so check that out. And then I included the links to the FireEye blogs, both the Qualcomm-related vulnerability and the Lenovo Vibe and other Lenovo devices at the bottom. And with that, I wanted to see if anyone had any questions. I know everyone's antsy to get to lunch, but does anyone have any questions? So let's do your front.
Which OEM do you think is the best for security? Like
Google.
Other than the
I mean,
Google phone?
Yeah.
A Samsung phone or?
Samsung's very good, actually. Samsung would be I think my second pick. So the Google cares a lot about this, and the Nexus series, the Pixel series, is what I own. If anyone is like, hey, I want to get a new phone, just buy a Nexus, buy a Pixel. That would be my recommendation. Samsung also cares a lot. The other Korean manufacturers are less good. Sort of LG, kind of they're not very good at all. They're receptive, but they're just not quite on the level of Samsung. And then you're at a whole different ball game when you dive into some of the Chinese ones, like Xiaomi, Huawei. Those ones just really aren't as good. They're actually getting a lot better. The Huawei Honor I was messing with earlier this year was actually much better than I thought it was going to be. I think it's the Honor 7N or something. It's very good. I had the Xiaomi 5, the Mi 5, and that one was not very good. I have a bunch of bugs on that. It was hard to get a hold of the Xiaomi guys to report. But anyway, they're a whole tier below, I would say. So it's like Google, most of the Korean OEMs, and the Chinese ones.
You mentioned heavily modified AOSP. How do the lineages, resurrecting remixes, things like that do on that case?
Can you repeat the question? Sorry, the last part.
The open source distribution of Android, your lineage, your resurrection remix, do they modify or do they in general keep SE Linux performing, SE Android performing, right?
So they're forking the project, and they're usually pretty supportive of things like SE Linux and stuff. They usually make changes as well. That's a question I get a whole bunch when I talk about the OEM stuff. They're always like, well, how about like CyanogenMod? What are they doing? And the question is, I really don't know. I'd love to spend more time like actually looking at what versions of CyanogenMod or all these other variants and things like that are doing. My guess is they're also not quite as good as Google, but I don't know. I would imagine that they're doing their best, and they're probably keeping it on here, because I think all those OSs want to, they want to still have the Google Play services, so they still need to use things like SE Linux, I think. Maybe they're not, because you're installing it on afterwards. But the short answer is I'm really not sure exactly what they're doing. That's one area that I want to get more into, actually.
So this might be in a similar vein as the last question. I'm curious if you've ever looked at anything by OnePlus.
I actually haven't looked at OnePlus. I just don't have any OnePlus devices, but I actually would really like to. They have their own, it's like Oxygen OS, or what do they call it? They have like their own fork of Android. So I haven't looked at theirs either, but it's very similar. Like they're forking off it, and they're doing a lot of changes that if I get my hands on one of those phones, I will definitely find some stuff, I think. Any, yeah, over?
Well, actually, I found that too was the prison phones.
Yeah.
Have you seen anything with those?
No, so really what it comes down to is like, what phones do I want to buy? Because work is like supportive, but they're like, hey, you can only buy like this many phones a year. So I have like hundreds of phones just like sitting in like my closet and stuff that they're like brand new phones that I probably should sell, but I buy them and I poke around with them, and then I'm like, I'll just work on this one. So it's really, if someone has like a prison phone, I'd love to look at it. What phones? I guess I looked at like, I actually really liked BlackBerry's phone. So BlackBerry came out with the, what's it, Priv a few years ago, like 2015. That's actually the phone that I found the Qualcomm bug on, so I was like so excited. I'm like, oh man, I hacked the BlackBerry. And then I'm like, oh wait, it's like every phone. But that phone was really good. Like those guys, they must have hired like a really in the weeds SE Linux guy, because that was actually what got me started on all this research. Is like I got the Priv by BlackBerry, and I'm like, man, this thing is like a rock. Like, what is going on here? And then I realized all this SE Linux stuff was getting in the way. And then I would like try it on like a Nexus, and I'm like, man, this is actually like way better than what Google even started with. So I guess to answer your question a little better, BlackBerry is also very good, but they only have like one phone every other couple of years, and I don't even know if they're making phones anymore. But yeah, but sorry. Any other questions? Yeah.
You say, or you said up there about that with the changes, it greatly complicates hacking it or breaking it for an attack surface. Greatly complicated, meaning that there still could be a possibility of breaking it?
Yeah, absolutely. I mean, I think any step making it harder is a good step in the right direction, but unfortunately, I just don't think, like an unhackable phone is a pipe dream in my mind, right? So like, for me, the harder they can make it, and the harder they can make it without a user even knowing, I think is also a good idea. But I mean, yeah, look at the Qualcomm thing, which worked with SEAndroid, the Lenovo one works with SEAndroid. Like this also isn't the only feature that Google's working on, right? Like things like the Verity, which I didn't even talk about, has really changed the scene as well. That provides a secure boot and secure boot framework. There's a lot of other things Google's doing as well, just to make this the threat landscape smaller. But yes, it's always going to be a problem in some way or another.
Cool, thanks.
Yeah.
So this addresses, exploitation and getting, privileges on a phone, but, what I hear about Android a lot is that, apps have a lot more access to information than they should. Just probably doesn't address all of that, but I'm just curious your thoughts on that.
Yeah, I mean, I think that's a concern. I think the developers probably aren't aware of exactly what function calls and app permissions they need. So they probably just read a Stack Overflow article and learn about like needing to give the right phone permission or something, and they're very loose about that. The other thing too is with that whole model, you're trusting the OEMs, right? You're trusting that in order to get the phone number, I have to provide the permission to do that. Guarantee any phone on the market right now, there is a bypass for reading the MEID without the permission. Because someone's going to write an API, because I guess I don't know why, but they're going to write an API and they're not going to subject to the same permission constraints. So the model kind of falls apart when that's like fundamentally broken. I think the permissions are great because it does help the user understand what the app can do, but I don't think it really denotes an entire security boundary. It's a good question though. Yeah.
So you mentioned that even once you got higher privileges, it was hard to change like the SE Linux policy. What would you actually have to do to change the SE Linux or SEAndroid policy?
You'd probably need the ability to load a kernel module that in the kernel either like overrode structures or disabled it from the kernel. So you would need code execution, not just as the root user, but in the kernel to flip that bit back over. So some sort of kernel home. Yeah.
What kind of privilege would you need to just be able to change the context on files?
Kernel. Because I guess you could technically, overwrite the policy file, right? So if you could somehow remount file systems and overwrite the policy file or the labeling files, that would be an attack vector there. The problem is those are all stored on the system partition, and because of the Verity, that partition cannot change or the phone won't boot. So that's, like I said, more features here. The idea of like persistent like bootkits or backdoors on Android are kind of dead because you'd have to also disable the Verity, which is way harder and requires a bunch more things because you can't make changes to sensitive files anymore. So like even installing like the SU binary is a trick now because they have to have like a new file system for it because they used to just throw that guy on the system partition and then now you have the SU binary, but you can't do that anymore because the phone won't boot. It's like, hey, this is wrong. But yeah, you do need more privileges then, so it's probably worth it. Yeah.
Does Google do a bad job of embedding apps on your phones?
I don't
Or does it do any, like Apple does some kind of vetting process that gives you a little bit more confidence on the iPhone about their apps?
I think Google does. I mean, I honestly can't speak to exactly what they're doing just because I don't have a lot of visibility into that. I mean, they are doing things, but is it enough? Maybe. A lot of it also comes down to, I have a lot of phones that aren't Google's sponsored or approved, which means they're using third-party app stores, and who knows what they're doing, right? Like, excuse me, a lot of the Chinese phones have their own markets, and you have a whole different ballpark when that's not what Google intended for things to do, and I think that is probably more of a risk to me, is having these other markets that don't go through the same scrutiny. So I think Google does that for some things, but I imagine if I wanted to, I think I could get malware in the store. I wouldn't do that, but if I wanted to. What are we time? We okay on time?
You got one more question.
Okay, I'll just do one more question and then.
So I know that you can do encryption on an app-by-app basis with AppLocker. Does that really help with security from this perspective?
I think, it helps in terms of like this vein and this like whole thing I'm talking about here, probably not. But for like definitely for like data and rest and stuff, like actually they're changing how encryption works too. They're actually going to a more iOS-like model where there's like a key that derives other keys, which then are used on like a per file basis. That's like I think new with Oreo, but I don't know if it's going to affect this process because all this stuff is going to be once the phone's on and running and once that also is transparent to the OS at that point. But I'm sure it helps though, like everything helps, right? Anything they can do to make this harder. Okay, great, and then that's all the questions here, guys. This is my contact information. Again, my emails if you want to talk to me. My Mandiant email, it's on there, but also my personal email, my Twitter, tweet at me. I'll try to figure out how to retweet things. And just some of my other stuff, like the Fire Research blog. I try to post stuff on there whenever I get to do cool stuff. My blog, my website, my GitHub, those are all on there as well. So thanks for joining us. Hope you guys got something else.